Good morning, students. In our previous class, we discussed about hydrogen spectrum. Even we discussed the different numericals based on hydrogen spectrum. Even at the end of the class, we discussed about how to count the number of spectral lines. Okay? Now regarding the calculation of number of spectral lines, and we got I given one or two formulas related to that. How to find the number of spectral lines directly. What formula we discussed there? When the electron is jumping from any higher energy level to lower level, any lower level, then what is the formula we discussed? It is n2 minus n1 into n2 minus n1 plus 1 divided by 2. Okay, so this formula we are going to use when the electron is jumping from any higher level to any lower level. Okay, even to make the above formula easy means when they are asking question based on when the electron is jumping from any higher level to first orbit. Okay, first orbit means what? N1 value is 1. So the above formula became n into n minus 1 by 2. Okay, where n means from any orbit. Okay, when we are going to apply this formula, when the electron is jumping from any higher level to ground state, first level. Okay, so in such cases we can use this formula, right? So these two we already discussed in the previous class. Even we saw one or two numericals also. Even based on this calculation of number of spectral lines, sometimes they are asking us to calculate in a particular region. Okay, particular region or particular series. Okay, in such cases, how to calculate the number of spectral lines. Okay, understood first about what we are discussing. For example, when the electron is jumping from fifth orbit to okay, it is jumping from fifth to first means we will find a different spectral lines. Either 5 to 1, 5 to 4, or 5 to 3, or 3 to 1, 2 to 1. Like that, different spectral lines will observe. Okay, so to calculate the total number of spectral lines, we are having this formula. If they ask that when the electron is jumping from fifth orbit to first orbit, how many spectral lines are observed in a Lyman series? And then ask you to calculate in Balmer series. Got it? Like that also they will ask. In such cases, we are going to use the formula simply as n2 minus n1. Okay? n2 means the higher level, n1 means the lower level. Okay? So for Lyman series, n1 is 1. For Balmer series, n1 is 2. Like that. Okay? So note down clearly in the notes first. Number of spectral lines in a series or in a region, because sometimes instead of asking a particularly Balmer series or Lyman series, they may ask how many lines are observed in UV region or how many lines observed in visible region. Like that, such type of questions also they are asking. Okay, because content is same, what formula we are using, everything is same, but the way of asking question is different. So when we face such type of questions first time, we may feel we don't know. Okay, so that's why giving this. Even while writing in the notes also, write clearly. This formula we are going to use to calculate the number of spectral lines in a particular series or the number of lines observed in a particular region. Region means UV region, visible or IR. Right? So in these cases, the formula is n2 minus n1. A simple formula, right? And let us discuss one or two numericals, then you will get even more clarity about it. So note down the question. So yesterday I think 4 or 5 examples we discussed. So let us discuss the next example. Find the number of lines observed in Lyman series when the electron transition from fifth orbit, okay, fifth orbit to ground state, fifth orbit to ground state of hydrogen atom. Okay, even in the previous class we discussed some examples. This question is different from those examples, right? In what way it is different? In the previous cases, in the previous last two numericals what we discussed, in that case we discussed or even you solved how to calculate number of spectral lines observed when the electron is jumping from fifth orbit to ground state of hydrogen atom means what? First orbit. Okay, so when the electron is jumping from fifth orbit to first orbit means the total number of spectral lines we calculated using the formula n into n minus 1 by 2. Okay, so we will get a total number of 10 spectral lines, right? But if they give the option as 10, can we choose that? No, right? Why don't we choose the 10? Because in this question, they are not asking us to calculate the total number of spectral lines. Okay, so they are asking us only to calculate the number of spectral lines observed in Lyman series. Okay, so what information we know about Lyman series? Right, Lyman series means we know the first series. Lyman, Balmer, Paschen, Brackett, Fun, even Humphrey also. So out of the spectral series, the first series is Lyman series. What are meant by Lyman series of spectral lines? The spectral lines observed when the electron jumping from any higher level to the first orbit. Okay. So in the case of Lyman series, n1 is 1. Okay. Got it or not? If they give Balmer series, n1 is 2. Paschen, n1 is 3. Now they are asking in Lyman series the number of lines they are asking. So what is the formula? n2 minus n1. Okay? n2 how much? They given n2 as 5. Okay, fifth orbit. So 5 minus 1. So the number of spectral lines observed in Lyman series is 4 lines only. Okay. The total number of spectral lines observed when the electron jumping from fifth orbit to first orbit is 10. Okay. But particularly in the Lyman series is only 4. But note down another question. I hope now you understood how to calculate the number of spectral lines in a particular series. Now solve this question. This is a previously asked question in the NEET examination. No. Calculate the number of spectral lines observed in Balmer series when the electron is jumping from fifth excited state to its ground state in hydrogen. Okay, so whatever the atom it may be, look at the question carefully. Asking to calculate number of spectral lines observed in Balmer series, and the electron is jumping from fifth excited state to ground state. As we know, ground state of hydrogen atom is first orbit. Okay, so in the case of Balmer series, as in the previous question I explained to you, Balmer series means what? The electron is jumping from any higher level to the second orbit. So in Balmer series, N1 is 2. Okay, so what will be your answer? 5 minus 2, 3n. That is a wrong answer. Okay, why it is wrong answer? But formula given n2 minus n1 I given. So n2 is 5, n1 is 2, 5 minus 2, 3 you may choose. That may be the first option. You may think we answered correctly, but later after checking the key only will come to know 3 is the wrong answer to this question. Now once again you cross check the question, then you will come to know why 3 is wrong. Okay, because if you observe the question keenly, I didn't mention it as a fifth orbit. Okay, so what I mentioned here, the electron is jumping from which one? Not from the fifth orbit. It is jumping from fifth excited state. Okay, I hope every one of you may have clarity about what is meant by the excited state. Okay, excited state means what? The higher energy level of the electron. Right? We know in the case of hydrogen atom, the electron is present in the first orbit. Okay, what will be its first excited state? When it jumps to second orbit, then it is its first excited state. Okay, so second excited state means when the electron jumps to third orbit. This is to the fourth, this is to the fifth. Okay, when the electron is jumping to fifth orbit, then we can say it is a third excited state. Okay, fourth excited state. Now when the electron jumps to sixth orbit, then this will be the fifth excited state. Okay, so when the electron is in the first orbit, when it jumps to its second orbit, then we say it is the first excited state. So second orbit is the first excited state, third orbit is second excited state, fourth orbit is third excited state, fifth orbit is the fourth excited state, sixth orbit is the fifth excited state. Okay, so that is why while answering the question asked in the national examinations, we should be careful. The content is same, The way of asking question they may make it difficult. So because in a hurriedness, we may think by looking at the number 5 on line Balmer series, immediately we will go for 5 minus 2, 3. There will be no mistake. Okay? So read the question carefully. They mentioned it as fifth excited state. So fifth excited state means our electron is present in the sixth orbit. Okay? So fifth excited state means orbit number is 6. Now the electron is jumping from 6th orbit to the ground state. We don't want to calculate the total number of spectral lengths. We want to calculate only the number of spectral lengths observed in Balmer series. Okay? In Balmer series, number of spectral lengths is equals to, as we know the formula as n2 minus n1. So nothing but 6 minus 2. So we will find 4 number of spectral lengths, and the electron is jumping from 6th orbit to 1st orbit in the Balmer series. Okay? So if they ask total number of spectral lengths, we know how to use the formula n into n minus 1 by 2. Because the electron is jumping to the ground state. So we will go for the formula n into n minus 1 by 2. Right? Total we will get 15 lines. But out of the 15 lines, these 4 lines are observed in the Balmer series. Right? I hope you got clarity how to solve these type of questions. Okay? Now, to the above question, I am going to do a small change. Okay? Same number of spectral lines, fifth excited state to the ground state of hydrogen atom is same. But this time, instead of Balmer series, my question is, okay? Now this time, I am not asking in Balmer series. Now I am asking you to calculate the number of spectral lines in infrared region. Okay? We are able to solve this. I hope you are able to do. But let's observe carefully. Infrared region. Regarding infrared region means near infrared, middle infrared, as well as far infrared. Okay? Mainly up to the fund series generally we observe, because our excited state is 6th orbit, so that is why considering up to fund series. Lyman series is observed, Lyman series of lines observed in UV region, Balmer series of spectral lines observed in visible region, Paschen series of spectral line, Paschen series of spectral lines are observed in near infrared. Bracket series of spectral lines in the middle infrared. Fund series are observed in far infrared region. Okay? So in the case of Paschen series, N1 is how much? Lyman, Balmer, Paschen, third series. So N1 is 3. So in this case, N1 is 4. Okay. Some of you may get doubt, sir, why don't you write Humphrey series? Because Humphrey series means N1, that is also in infrared region only, right? But that in the case of Humphrey, M1 is 6th. So 6th orbit only. When the electron is in the 6th orbit, it cannot jump back to 6th orbit. Okay? So we cannot find spectral lines in Humphrey series. Okay? If the electron is in the 7th orbit, then okay, we should count Humphrey also. Okay? Understood? A typical question. This was also a previously asked question. Observe them carefully. They mentioned simply as infrared region. Infrared means Paschen series, bracket series, Fund series. All these three series of lights will be comes under infrared region. Okay? Now first of all, let us calculate number of spectral lines in Paschen series. What about the formula? We have N2 minus N1. N2 is how much? The fifth. Anyway, in the previous question we solved. Fifth excited state means the orbit number is 6. So here the number of spectral lines is how much? 6 minus 3. In this case, 6 minus 4. In this case, 6 minus 5. So the total number of spectral lines observed in infrared region is 6. Okay? When the electron is jumping from 6th orbit to the ground state, the number of spectral lines observed in infrared region is 6. I hope you understood how we solved this question. Okay? The first thing we need to focus, we should have clarity why I have taken these three regions. Because infrared region means all these series of lines will be observed in infrared region. Okay? Then second thing we need to focus why I have taken n equals to 6. About that in the previous question we discussed. A fifth excited state means the electron is in the 6th orbit. Okay? Then we have done. Right? I hope now you will be perfect in solving the questions based on the number of spectral lines. Right? If not, even you try to solve this question by your own. Calculate the number of spectral lines in observed in visible region an electron jumps from ninth excited state to its ground state. Okay? Same thing. The number of spectral lines observed in the visible region this time. Okay? When the electron is jumping from ninth excited state to ground state. Okay? Now you got clarity. Ninth excited state. Nothing but what is the orbit number 1? It is very clear. Ninth excited state means 10th orbit. First excited state means 2nd. Fifth excited state means 6th. Eighth excited state means 9th. So ninth excited state means the electron is in the 10th orbit. So very clear the higher energy level is 10th orbit. What about the lower energy level? They given the information that the electron, so we have to find the number of spectral lines in visible region. As we all know, Lyman series is observed in ultraviolet region. Balmer series of lights are observed in visible region. So visible region nothing but Balmer series of lines. So in this case, the electron is jumping from any higher level to second orbit. Okay. Now what about the number of lines? Our formula is same, n2 minus n1. So 10 minus 2. So the number of spectral lines observed in visible region when the electron is jumping from 9th excited state to the first orbit. Okay. So these are the maximum different model questions based on calculation of number of spectral lengths. Okay. The 99% you will get question based on spectral lengths. These are the maximum models. Okay. Even in the previous class, we discussed about direct model questions to find wavelength or frequency or wave number of a particular electronic transition, right? Even let us discuss one or two other model questions also based on the calculation of frequency or wavelength, wave number or wavelength of the hydrogen spectrum. So first note on this one. Note down the question. The longest wavelength line in helium plus of Paschen series is okay. The longest wavelength line in helium plus of Paschen series is M. Then the lowest wavelength line in Paschen series of lithium is how much? Okay, instead of lithium, let us take helium. Okay, so let's look at the question. The longest wavelength line in helium plus of Paschen series is given as M. Now the question is then the lowest wavelength line in Paschen series of beryllium plus 3 is how much? These options they given in terms of M. Okay, this is also a previously asked question in the national examination. Because direct model questions we already discussed in the yesterday's class. So let us discuss some typical questions, different model questions. Now, first coming to the first data, longest wavelength. Okay, they did not mention which line. Means if they given simply fifth orbit to third orbit, how to solve the question? You have already done many times, right? Okay. So now this time, longest wavelength. What is the relation between energy and wavelength? We know energy inversely proportional to wavelength. Okay. So longest wavelength means lowest energy. Longest wavelength is nothing but the lowest energy line. Lowest energy line in any series is which one? The first line. Okay? The first line is having requires lowest energy when compared to last line. Okay? So it is nothing but the first line of which series? The first line of Paschen series. What is the first line of Paschen series? Lyman, Balmer, Paschen. So in Paschen series, N1 is always 3. The given one tabular form, you check it from that. N2 is what? 4. This is the first line of Paschen series. Okay? Now, this line wavelength is given as M. Okay? Now, first of all, let us write the formula to calculate wavelength. What is the formula we have? 1 by lambda is equals to RH into 1 by N1 square minus 1 by N2 square into Z square. Okay? So which atom they given? Helium. Right? For helium, atomic number is 2. Let us substitute everything. Lambda value they given as M. I am not substituting the value because anyway it is comparison. And the options are given also in terms of R. 1 by 3 square minus 1 by 4 square into the atomic number of helium plus is 2. So it is 2 square. Right? Now, if you observe there, the 1 by M is equals to R into 1 by 9 minus 1 by 16 into 2 square means 4. How much it is? 1 by M is equals to R into, so after taking LCM, how much will come? 16 minus 9. So it is 7 divided by, it will be 36. Okay, so 9 into 16, but 4 will be cancelled 16 4 times. So 9 4s are 36. I know you were able to do those multiplications and divisions. Okay, understood why we got this 36. First of all, LCM 16 minus 9, 7 divided by 19 into 16. In 16, 4 will be cancelled 4 times. 9 4s are 36. Let it be equation 1. Okay. Whatever the first data they given corresponding to that whatever equation we got, let it be equation 1. Now, coming to the second data, the lowest wavelength line. Okay, lowest wavelength, nothing but highest energy. Highest energy means what? The last line. So last line. Which series? Same series. Paschen series. What is the last line of Paschen series? For Paschen series, N1 is 3. Last line is which line? Electron jumps to infinity. Okay? And directly let us substitute. In this case, 1 by lambda is equals to R into 1 by 3 square minus 1 by infinity square. Atomic number of, I think, beryllium they given in the second data. Atomic number of beryllium is 4. Okay, so 4 square I will take. How much it will be? So 1 by lambda is equals to r into, we know 1 by infinity means 1 by infinity is 0. So 1 by 9 into 16. So we'll get 16 by 9. Okay. Let this one as equation 2. Okay. Now I am going to do equation 1 divided by equation 2. Understood? Equation 1 divided by equation 2 if you do, what will become? Equation 1 is what? 1 by m divided by equation 2 case we will get 1 by lambda is equals to r into 7 by 36. Equation 2 case it is r into 16 by 9. Okay. So what happens here? Lambda will comes to the numerator. So lambda divided by m is equals to r gets cancelled. So 7 by 36. This when comes to the numerator it will become ulta. So 9 by 16. So 9 cancel here 4 times. So finally lambda is equals to what is left in the numerator 7 divided by 4 into 16 54 m I got this side. So this is the option we should choose regarding this question. Okay, so not a different model question, but previously in the yesterday's class we discussed how to calculate wavelength or wave number directly by substituting n1 and n2 values. This time, comparison between two species they ask. Okay, the first data regarding helium and the next data regarding beryllium. Okay, understood? So whatever we know, simply we substituted in the formulas. Then finally we did equation 1 by equation 2. Then we got the wavelength of this beryllium, sorry, the lowest wavelength of Paschen series in beryllium is 7 by 54 times of m. Okay, the m means the data of the